Hello and welcome to the Build Better Homes podcast. I'm your host, Royal Mortier, and today we're doing technical topics. So in technical topics, it's going to be just me, my co-host John, although he has a lot of technical knowledge in construction. I try and focus this podcast more on technical items in terms of engineering. We'll probably have him do some technical topics down the road to discuss architectural and constructability elements. And as we add more experts to our Clears forensics team, maybe we'll hand off that mic to them as well. But for now, you got me discussing structural engineering items. So this is going to be a fun one, something that affects all home builders. And so I really hope this gets spread out. And as a home builder turned engineer, I had this difficulty as well constantly when I was building homes. And the joke goes basically, if you ask an engineer to find a solution to a problem, if you ask 5 engineers to find a solution to the problem, you're going to get 5 different answers. And we noticed this also when I was building homes, is I could send what was essentially the exact same home to 3 different engineers and get 3 different designs. And those designs varied as far as the amount of labor and expense that was necessary in order to complete the home. And so what I want to talk about today is how basically an engineer does or should go through the process, especially how it applies to single family residential, or more importantly, overall, the broader of wood construction. First and foremost, the engineering of a structure is really broken down into 2 steps. And that is determine the load and resolve the load. So determining the load can be simple, or you can make it as complex as you want to be. And determining of loads is all governed by what is known as the ASCE 7. Here's a paper copy this is the ASCE 7-10. This is the last physical copy I have in my library. We've since gone paperless, so everything's electronic now. We now have an ASCE 722. But for the majority of the United States of what we engineer with wind and seismic, those elements have been pretty standard for quite a while. They make minor variations to them. The largest one was recently, where they took out multipliers that were already built into certain factors, and they pulled those out. So they're an extra determination factor, which again, in its application to low-rise construction, low-rise wood construction, not massive differences, but definitely as you get larger. I mean, this loading determination applies to everything. ASCE 7 applies to everything. It applies to general structures. It applies to signs. We determine seismic and wind loading, hurricane loading, tornado loading. Everything can be determined and guided by the ASCE 7. If we're designing a water tank on top of a building, like, it has everything but determining what that load imposes on the building, how to resolve the load, how to connect it to the building, everything like that. So that's the ASCE 7. Then once we're resolving the load, then every other design code comes into question. And that being whether it's steel, concrete, wood, how we're designing it, and then all of those different codes come into implication. So that's how we go from there. So now resolving the load is its own finesse, because the other thing that comes into that is how much construction experience does the engineer actually have? Are they accounting or considering the constructability of what they're resolving? How much cost and understanding of cost of that construction do they bring into the equation? So that's where it's always important that I say, when there's almost a third step, which is determine the load, resolve the load, and then the final step is review for constructability and conflicts. That final step, or value engineer it, that final step is very, very important. And having experience and knowledge in construction is very helpful. And when I ran or worked on large commercial sites, we had what was called the RFI process, or even a VE process, where we would go back to the engineer of record and say, hey, I get it that you designed it this way. However, we can save the project a lot of money if we could tweak this, edit that, revise that. One of the ones that echoes the most in my mind was a large bridge project that we were building. The engineer had specified these massive, massive caissons, massive steel caissons. I think 10, 12 foot diameter steel caissons. And the contractor, at that point, I was the owner's rep. The contractor came to us and said, hey, you guys have these massive caissons specified. We can save a significant amount of cost in materials if instead of this, we go to a smaller caisson, like a 2 to 3 foot diameter, and we do way more of them. And the contract, the VE savings was split between the contractor and the owner. And they proposed a pretty significant savings in the point of like millions of dollars. And they also said, hey, we will cover the engineering for revising it from these large caissons to these small caissons. And the engineer of record wasn't having it. We went to them as the owner saying, hey, this would save us money. The contractor pleaded with them. We had multiple meetings, and they basically just checked out of it and just said, build it how we designed it, and moved on with life. Unfortunately, we have a lot in the engineering world. We have a lot of that mindset where the engineer is almost either overwhelmed with work, so they don't have the time to go back through it, or they are just have the ego to say, hey, you're basically you questioning my design or trying to be the design. You're saying that my design is bad. And us as engineers need to not take that mentality. We need to work in junction with our contractors and say, okay, well, let's see how we can make this more cost effective. And let me take this as a learning experience and move forward. So the reason I'm bringing this up as a topic is it was brought up as a question with some other engineers I follow on social media. And they brought up the fact of clients commenting, oh, well, my stuff is over-engineered. And, you know, we do get those comments of like, oh, I think what you did is over-engineered. And the common retort or kind of the stance we take is, again, we determine the load, we resolve the load. If you have a better way of resolving the load that we've determined, let's discuss that. But to say, oh, it's over-engineered, maybe that's not the case. Or more commonly, and this is what we're going to discuss today, is the engineer isn't accounting for all ways to resolve the load. And as it applies to wood construction, we've seen it firsthand of engineers kind of going with a systematic approach to resolution of loads in wood construction. And the fact of the matter is there have been advances in wood construction, or there's additional design abilities that an engineer can use in order to resolve load that may result in cost savings to the builder. So when we're resolving that load in general wood construction, we have to resolve the vertical forces or your beams, and really from one engineer to the next, your vertical resolution should be identical if they are determining the load correctly. Okay. Beams and everything, that's vertical load. I make the joke that I could probably teach my kids how to determine vertical loading and resolve it. And the fact of the matter is you really can. It is pretty simplistic equations if you understand tributary area, determine what the load is, the tributary area of the load going to the beam, and the resolution of that. Then it's up to the engineer and the contractor to determine what material that we're going to use to resolve that. And that also becomes a constructability and a cost question, because like in the case of an upper floor system, we want to try and keep those beams hidden within the ceiling system. So we don't want them dropping down and obstructing a smooth ceiling appearance. So that's where we kind of come into the material selection for the loading and the span, and then the constructability aspect of it. Can we keep that hidden in a floor system? Or in some cases, if a wall is directly above it, push it up into a wall above. But lateral, there's a lot more to it. I'm going to focus on the two main loadings nationwide, which is wind and seismic. Okay. We have other situations where I'm here on the Gulf Coast. We have to also account for hurricane loading. If we're a little more north, there's this discussion of tornado loading and resolution of that. But in the grand scheme of it, we either are in a situation of high wind, high seismic, and how we resolve that. So let's discuss this. So what is the most common way to resolve a load by most engineers is what's called a segmented shear wall. Okay. There is a visual portion to this, so hopefully you guys can catch in on that. All right. So what we're going to discuss is segmented shear walls. Okay. A segmented shear wall considers a full width, unobstructed, not with no penetration, so no windows, no doors, section of wall. Okay. So if I have a wall, and let's say just a common kind of front entry wall, I've got a window here, I've got a door here, and I've got a window on the other side. Okay. And I'm actually going to make this wall a little bigger to account for that. Okay. So the code is very simple in this. A segmented shear wall is a section of wall that has no penetrations in it that's also full height. Okay. So then there's also what are called height width ratios. Okay. So if I have my height here and say I've got this window width here and this is unobstructed. So I've got a window width here. So this is 1, this is 2, I've got a width here. This is 3, and this is 4. Okay. So the height to width ratio is very simple. Okay. It's across the board. It's 2. Okay. No caveats, no reductions, no nothing. It's 2, which means very simply, if I have an 8-foot tall wall, I need a minimum 4-foot wide panel. Okay. And then I can take the complete shear of that in a segmented system. Okay. But there's a caveat to that, exception to that, which says if I am over that ratio, that I can still use that section of wall, but I have to take a reduction, which means that I can then go all the way up to a 3.5 ratio. Okay. So if I had a 9-foot tall wall, I can have less than a 3-foot wide section. I think it's 2'8", I think is what it works out to be. A 2'8" section on a 9-foot tall wall. And I can still use that section as a shear wall, as a segmented shear wall, but I have to take reductions to its capacity because it's considered what's called a narrow shear wall. Okay. But still, what's going to wind up happening, so let's say my W2 and my W3 don't meet that ratio. Okay. So my section between the window and the door and on both sides don't meet that ratio. That means all I can do is use this segment here, and then W4, the width, the section on the right side of the window, I can use this segment here. Now, both of these are going to wind up with hold downs. So I'm going to have a hold down here on both sides of this segment, and I'm going to have a hold down here on both sides of this segment. Okay. What has happened now is I basically only have 2 panels or 2 segments of the wall that are usable as a shear wall. And then each of those are acting independently. So I have to account for the fact that I have this situation of hold downs on either side. Okay. So this segment has hold downs. So I wind up with 4 hold downs on this wall section. Okay. That's segmented. All right. Now we're going to kind of draw basically the same situation here in which in which I have a standard entry wall here. Okay. I've got a window. I've got a door. I've got another window. Okay. Keep doing this. Keep making that one way too narrow, don't I? All right. Okay. So now we look at this and go, okay, and I'm actually going to draw these windows a little differently. Okay. So now we can look at this and go, okay, well, I have these windows and I have sections of wall above and below the window and adjacent to both sides of the window. Why can't I use those? And the fact of the matter is you can use those for lateral resistance. And that takes us from a segmented shear wall assembly to what's called a perforated shear wall assembly. Okay. And so what a perforated shear wall assembly does is basically says, hey, you've got this penetration through the wall that takes away some of the shear capacity of this wall, but it doesn't make it zero. So why not just reduce it by a factor based on the ratio of that window opening to the actual area of the wall or even the area of the door. So that's called a CO factor, and it's a reduction factor that we account for. There are still our limitations that we have to look at for the ratios, but we can say, hey, I've got a window, I've got a door, I've got this thing fully sheathed. This whole wall is fully sheathed. So what allows us to do is say, okay, well, I may be able to resolve the load just here, just on one side of the door, and so I'm just encompassing a window, or if I needed the entire wall, I can account for the reduction factors for all of the openings as a relative ratio to the overall area of the wall. So now my shear wall becomes everything that I've sheathed. So it becomes all of this. And so now, in the case of a lot of states where we already fully sheathe our walls to properly account for the siding and provide backing for the siding, we can now account for all that sheathing using a perforated shear wall. Now, I will say we work in states where stucco is very common and the builders are trying to save on plywood. And so we do what's called selective sheathing, where we will go through. And so in this case, we may look at this and go, well, hey, I don't need this whole wall sheathed in order to resolve the load. I can just, from the corner to say the door, I can just sheathe that section. And then the rest of the area gets like a fiber type board material that they put on instead of the more expensive plywood material. So then we would just be looking at sheathing this smaller section, resolving the load, even though we have a window, and then the rest of it can be the fiberboard. But regardless of what we wind up with, we can still account for the fact that we're putting in sheathing and we have some windows, but there's sheathing above and below it. And then what winds up happening is if we do that, instead of say the upper section where we've got multiple segmented shear walls, where each segmented shear wall has a hold down on either end, we now can wind up with just a hold down at the very end. So we just went from 4 hold downs to 2, which is great. Okay. So this is segmented. The upper one again is segmented. Again, I'm learning my whiteboard. So appreciate your patience as I learn how to use this really cool tool. And I hope it's beneficial. So this is segmented. This is perforated. We'll just abbreviate that. Okay. Now there is a third prescriptive shear wall that we can engineer with. Okay. And I'll go back to what I mean by prescriptive. Okay. So there's a third prescriptive shear wall that we can use. And that third prescriptive shear wall is what's called a force transfer around opening, or FTAO. Okay. So where this comes into the discussion is, let's say we have a wall. We've got windows and a door. We got another window. Okay. But you'll see I've drawn these windows pretty large. So the segments adjacent them are pretty small. Okay. And I did this for a reason, because this also becomes common in a front entry condition or in an area where now what we're seeing is jurisdictions actually requiring a percentage of openings based on the front of the building. They're encouraging or pushing for the fact that they have to have more window openings to increase the aesthetic, not just be a four-sided box, right? With, just a small front window, an egress window in each bedroom, and a window in the bathrooms. Like, they're trying to encourage the use of more openings. Okay. So what we wind up with, unfortunately, these segments may be too narrow to meet the ratio. So that 2 or 3.5 ratio, we just can't get to it. And so this is a great tool that we use in that situation. We also use it when the forces are so high on a wall that it's pushing us into a hold down that is either A, significantly more expensive, or B, cannot be retrofitted. Okay. So there are hold downs or vertical forces, tension forces that go into a hold down that when they get to a certain point, we either have to beef up the stem wall, go to custom built embeds because the forces are so high. And with that, the forces are so high, if the contractor was to set the hold down incorrectly, or it was to be damaged, which does unfortunately happen, there is no retrofit for it. It is take out the section of concrete and re-pour it. And that's very time consuming and expensive to the contractor. So we implement this in considering constructability, and that accidents do happen, as an alternative to doing that. Okay. So again, ratios or just the tension forces are so high. And so what an FTAO is this is, and you've probably seen it driving around job sites, especially on like multi-story apartment complexes, but we actually put a strap across the top and the bottom of the window. Okay. We have this strap going across it, and that functions as a drag or a collector. So for the typical wall, the top plate and the bottom plate function as that, just under natural construction conditions. But what we found through testing and the development of this is by putting that strapping and providing blocking in the back, it serves the same purpose. And so now what winds up happening is, instead of having to take the full height of the wall in consideration for our ratio, we actually take the height between the straps, which is basically just the height of the window. So now, let's say I've got a 9-foot wall and I put in a 5-foot tall window. Now for me to meet that ratio, my height that I'm considering is now 5 feet instead of 9 feet. So for me to meet that 2 or 3.5 ratio, I can do that with a much narrower wall section. Okay. And so by doing this, it does a few things. So one, it brings our height down in our ratio, which is great, because let's say we were at 3.5. Now I put those straps in and say it gets me under that 2 ratio. Now I don't have to take any reductions on my shear wall. Okay. It also shrinks my height down that I have to account for in the tension, what's called the tension compression couple. So if I have my forces being pushed up here initially at the top plate, I now can actually account for them pushing right here at my strap, because this is now functioning as a collector. Okay. And then I'm actually looking at them being resolved based on the height of my window, not the height of my wall. So in doing that, it also reduces the tension force that's on there, because when I'm pushing on something taller, and we can think of this as the leverage equation, right? A consideration of leverage. If I'm pushing on something, let's say a box, and I'm able to get way, way high up on that box, it takes less force for me to push that box over. If I'm pushing at the top of a box and I'm trying to resist it at the bottom with a point, okay, the further away I get from that point, the more leverage I have. So the more force that base connection requires in order to resist that load, okay? So if I'm going like this, the higher up that force is, the more resistance I need on this side. If the force is pushing way up here, the more resistance I need on this side, okay? So by shrinking that down, I've reduced what my tensile force, my tension force is that I have to account for at these bottom points. Okay. Now the shear does increase in these sections, but if we can resolve that shear with just standard nailing, that's standard nailing. Standard nailing and sheathing, that's conventional construction. That's not adding any cost to the real project, right? Another stick of nails or another coil of nails on a sheathing project is not a significant amount of expense. So, but when we have extremely large embeds, custom made embeds sometimes, and a high tensile force to resolve, and beefing up a foundation and doing all those things, that can add a significant amount of expense. Not to mention these coils, the coil strapping we're speccing typically comes in 100, 150, 250 foot rolls that, again, not a very high cost per foot. So this is a great tool that honestly, I see a lot of engineers not using. Most of what we see coming from engineers for general residential construction is a massive use of segmented only with maybe some perforated mixed in. Okay. So again, this is the FTAO and just is a great additional tool that can and should be used by engineers. Okay. So in conventional wood construction, these are your three prescriptive, in that we have a code that says, hey, if you have these conditions, you analyze it with these factors, this is what your capacities are, right? And this is how much force you can resist, like per lineal foot or whatever the factors may be. So these are your three most common prescriptive wood construction shear resistance methods. Okay. There is a fourth, using, again, conventional wood construction, that is performance-based. And what I mean by performance-based, it is something that there really isn't the engineering principles to back it, to support it. So they've done a ton of lab testing on it. And that lab testing has resulted in us having capacities for these wall sections that we can look at and determine as engineers. And we're basically given a table which says, if you build it like this, this is how much capacity you get. Okay. And that would be what's called a portal frame. Okay. So here's a great diagram from the portal frame. The APA has done a ton of testing on the portal frame. Man, I keep on getting blacked out here, don't I? All right. So let me zoom this in here, make that bigger. Okay. So the APA has done a ton of testing on this portal frame system. And what they've given us is this envelope that we have to build it within. This portal frame has been adopted by the IRC. You can find it in the prescriptive path methods in the IRC. There's some other variations to it that the IRC, International Residential Code, has provided for us for reference. But vastly across the board, we're working in 30 states now. This is what everybody uses. Okay. So the portal frame initially was developed and put into use for around garage door openings. And that's still what it's used predominantly for, is garage door openings. And it allows us to have these narrow wall segments to then allow for a large opening for these garage doors. And then you can work with it there. We have used it in other situations where we had no other method. We've used it in like some townhomes where they're a narrow build in that actually 18 foot to say 26 foot envelope. And we've used them around the rear sliders just because there was no other real option, or there is another option, but it's much more expensive because it's a pre-manufactured system versus something that their framers and their concrete guys know how to build regularly. So this is something you guys can fully download. It's the APA TT100. And it's, like I said, it's been around for a long time, and it's very simplistic for the most part, but basically key points of it: max height is 10 feet, and that's from your top of the foundation to the top of your header. That's your max height because that's where the load is actually being resolved. Your overall height, you can then extend what they call pony wall, an additional 2 feet. So that is a limitation of this. You are 12 feet total from the top of your foundation to your top plate. So in situations where we have a hillside build, where say or we're putting in much taller doors, then in that condition, you are going to have to extend your stem walls up higher. And those stem walls are going to have to be custom engineered for the imposed loading if they get too tall in order to account for that. But you have that. You have a minimum header size, which most commonly builders just use a 4x12, but you can use a double 2x12 if you splice it together and nail it together significantly. Your rough opening width, maximum of 18 feet. So again, when we think about this, where this really came about was people were trying to figure out how to put in a 16-foot door in a 20-foot wide garage. And when you think about it, the old size of a portal frame across the board was told to us as 22.5. And for my old framers listening, you'll remember that. You guys remember that number. Okay? Wing walls, 22.5. That's what it's got to be. Wing walls, 22.5. Okay. This has since changed that. So we can actually go all the way down to 16. But in the grand scheme of it, we have a situation that we can do, the more common one that we've known of is the 22.5. And that's because 20-foot wide garage, 16-foot door. Then you have your 1.5-inch trimmer on either side for the door, which gives you a 22.5-inch wing wall on either side. Okay. So we have our wing walls. We have a max wide opening of 18 feet. We have strap type hold downs. This is something, again, has come up as a discussion point. They initially went with strap type hold downs because Simpson said those were the ones with the least amount of deflection. I really, really hope APA tries testing this with a standard conventional in-bed hold down. They told me personally, they haven't even tested it. They haven't even considered testing it. But the issue with the strap type hold downs is if they're damaged, there's not much for retrofitting them. The retrofit that they do have really looks terrible. And so, especially if you have a conventional siding or you aren't covering everything with stone. So going with a standard embed is an option I would like to see. In addition to that, strap type hold downs get damaged way more often than an embed. An embed is going to have a 5/8 inch, 7/8 inch diameter anchor rod. It's pretty hard to bend one of those. These are like an 18 gauge or 14 gauge strap. And you're allowed one bend cycle, which is you can bend it, install it, you can bend it down out of the way, install all your wood framing, and bend it back in place. That's it. If you bend it more than that, the galvanizing starts to fall off. It starts to develop a crease in it. And honestly, the most common thing we've seen is the framing truck driving over the strap or somebody driving by it when it's in the bent down position and just pulling it right out of the foundation, or improper consolidation of the concrete where the strap actually embeds into the foundation. It's hard for the concrete to flow between the form and the strap. So multitude of reasons why these have issues. Really wish APA would do that. And I'll have to send this podcast to my guy at APA to help vocalize that. So anyways, great diagram of how this is constructed. And then we go down into here. And this gives us what our shear capacities are. So this is a table we're allowed to interpolate. So they give us, your portal frame height and your minimum width. And so we're allowed to interpolate between our heights and between our widths, which gives us some flexibility. But again, we can go all the way down to a 16-inch on our portal frame, going up to a 24-inch. And that's where our interpolation stops. If we go to a 32-inch, we can't go beyond that and go, oh, well, if we have a 32-inch, then it's this much stronger. That's not how that works. We're allowed factors in wind versus seismic design, tells us about approximately deflection and a multitude of other things. So overall, this is the most common used performance-based system. When we get outside of this envelope of what is allowed under a portal frame, then we're talking getting into a pre-manufactured option, which Simpson provides a bunch of strong wall options. We're seeing a lot more use of the Simpson in the case of townhomes and narrow builds and stuff like that, where it's just the fact of the matter is there's just not enough wall with the openings and stuff to resolve the imposed loading. So we have to go to another option. So that's those items. Now, I do want to touch on what is called prescriptive path, because prescriptive path has existed for a long time and is a great tool for builders, in which you basically are able to circumvent an engineer and just say, oh, well, my build complies with the prescriptive tables, and determine that. So how prescriptive path comes about is it uses the ASCE 7 for determining the load. It uses the wood design code for determining resolution of that load. And it comes up with a list of tables that honestly have some built-in factors of safety to say, hey, if you have this condition of this max spacing between your walls and your roof span is this wide and its, maximum pitch is this, then you can use these tables. And then from there, you can go, okay, I've used these tables and now I have ratios of my wall is this long. I can only have this many openings. I need this much wall at every corner that allows for me to have this. My shear walls are constructed out of this material. There's a lot of things to it. And in areas that are lower lateral loading, low wind, low seismic, especially low seismic, it can be useful. And it can be a cost-effective option as an alternative to using an engineer, because in the end, the engineer is probably going to get somewhere close to that. But it also puts you in a box of this is the envelope that you can build within. And so once you're outside of that box with anything custom or of any significant size, you no longer comply with those tables. Now, I will say this, in areas of higher seismic loading, pretty much anything above seismic design class C, which is a good amount of the United States, it's not a cost-effective option, and we can prove it. And John O'Shea, who is our COO of the company, when he worked for a builder, they constantly tried to use prescriptive path for their builds. They were a custom build on your own lot builder. And so they had their drafters trying to determine all of the ratios, all the loading, trying to make the building work within the envelope, only to have a significant percentage of their projects have to go to custom engineering only, because everything they produced was custom. So if you're a production builder of smaller production homes that can fit within the envelope, and you're building in areas that have lower lateral design stuff, great, do that. But I can show you on paper that you're probably putting in more shear walls than are necessary, more hold downs that are necessary, and taking a lot of extra work from your people and learning the prescriptive path code and learning all those ratios and learning those requirements to get that building to work within that envelope. So think about that. Like, engineering has gotten far more productive, is the easiest way to put it. There's more software, there's more tools, there's better There's better codes that give us different options. And if you're working with an engineer that understands those, it's really beneficial all around. But I had an engineer that used to work for me, and his comment about prescriptive path, it's like using prescriptive path is like playing a game where you learn the rules at the end. And it kind of is, because you have all of these boxes in questions that you have to answer initially about whether or not the home meets these requirements to even be considered for prescriptive path. And then you can go from within that and go, okay, well, only these walls meet prescriptive path. And so then you're using prescriptive path just for those walls. And then you're engineering the other walls, but you have to determine what the load is on the entire building in order to engineer those walls that don't meet prescriptive path. And then you don't even know if you can make those walls that comply with the rules of prescriptive path work until you go through all of the analysis to see if your ratios and everything already work out. So again, there's a lot of hoops to jump through with it. I can fully engineer a home probably quicker than whether I can determine whether or not it complies with prescriptive path. So there's, in that aspect of it. The other thing I want to hit on is the use of the tools that are available. So in a wall assembly, okay, I can just draw it up here. Okay, I have my studs. Okay, I've got my bottom plate, my double top plate. Okay, outside I'll have, say, we're going to get colorful here. I have my sheathing here and everything that goes along with that sheathing, your rain screed, your siding, all that stuff. On my inside of my wall, I'm going to have my sheetrock. Okay. Okay. So here's the other thing when you're actually engineering the home that I find a lot of engineers ignore. But there's tools and things available to us for us to account for it actually pretty simplistically. Okay. And that is, the code allows us to consider the shear capacity of the exterior sheathing, and in the case of wind, the capacity provided to us by the sheetrock on the inside. Now, where this becomes a complexity is in places where we have to analyze worst case scenario for every wall we're using as shear wall, in which the code for us as engineers clearly states that when we're applying a load to a wall, we have to account for the wind load and the seismic load, determine which one is higher, and then resolve that load accordingly. Because luckily the code doesn't say, hey, you have to account for the fact that wind load and seismic load may be happening at the exact same time, right? We basically choose one, maximum considered earthquake or highest wind speed, and go with that route. So what happens is when we're trying to resolve that load and say it's in a complex structure, we may have a situation where certain walls have higher seismic loading going to them than wind loading. And so then what you have to do is you have to ignore the contribution of shear from the gypsum on the inside, from your sheetrock. And that, again, adds a complexity. But there are tools available in people that, hopefully an engineer that's really focused on wood design is using those kinds of tools that allows them to easily account for the fact that, hey, this wall meets governed by seismic, so I'm just going to ignore the capacity from the sheetrock. That does affect things of like overall wall shear capacity, the deflection of those walls, and other elements like that. But when wind is governing, the sheetrock in its general installation pattern actually provides some shear resistance, which can save the builder from having to, say, add additional nailing, maybe going up from a 7/16 OSB to a 15/32, and a multitude of other things. So it's just something that kind of provides that buffer and a just in case we're somewhere on the threshold. Or in the case of, the more common one is going from like a 3/12 nailing to a 2/12 nailing, because when we go from a 3 and 12 nailing to a 2 and 12, not only did our nailing increase, but now our bottom plate size increased, the size of our blocking increased, the panel edge adjoining now have to be a double stud instead of a single stud. So sometimes that is the decider, is if I can account for that shear capacity for my gypsum, does it save me from having to jump to, say, a 2 and 12 nailing? So just something to consider on that. So, all right. That was a lot of information in 50 minutes. So I hope to have some follow-ups on these, but the key items from it is, look at your plans, look at this stuff. If you are an engineer and you're only designing with segmented, expand your horizons a bit. If you're only accounting for what you're getting from your sheathing, look at what you can get from the gypsum from its installation. If you're a builder only using prescriptive path, because, hey, then I don't have to use an engineer, understand that may be costing you money. And engineering, again, has gotten pretty efficient in production. So think about those things. And if you are a builder and you look at your plans and you're like, wow, I've got all of these hold downs and I feel like there could be a more efficient way, do talk to your engineer and, have that discussion of, hey, could we do a perforated? What about an FTAO around my front entry so I don't have to do all these other things and beef up this other stuff? It can save me some money. It can save me some labor. So think about those things. But hey, I appreciate you listening. If you enjoyed this, if you found it educational, please like, subscribe, share. I've had some builders reach out to us and they appreciate the information and education from it. I appreciate the fact you guys are listening. And, and if you are in a situation of you're looking at an alternative, feel free to reach out to us. We're always growing and we're always looking to build our team. And the biggest thing is we're in the service industry. That's what we do. We serve our builders. You builders serve the homeowners. We're providing a product, right? In order to be providing a quality product, you need to be service minded. You need to find that give and take. You need to be able to communicate with the people that you're working with and find a value engineered approach, something that's cost effective and still gets the job done. And that's all of this stuff that I just showed you here. And so always appreciate the chat. If you have any questions or if you have a technical topic you would like to discuss, please feel free to message us. All of our socials are monitored. Any of those questions or comments come straight back to us. Again, we always appreciate you listening. And the only thing we ask for in return is if you like the show, share it with your friends. Thank you guys and have a great day.